Let's prove that the limit as theta approaches 0 of the sine of theta is equal to 0, and let's do it by the squeeze theorem. Before we begin, let's review some basics. If we are going to measure angles, there are two different ways to do it. The first is the degree measure. For example, in a circle, there's 360, and we put the degree symbol there. Another way to do it, which we'll do in trigonometry and we will continue to do in calculus, is by the radian measure. The bonus to using radian measure is that the length of the arc subtended by an angle theta, as long as theta is measured in radians, will be equal to the measure of the angle. So let's see what that means. So on the left here I have a circle that I've drawn. I've centered it at the origin. This is just our xy plane. Okay. I can choose any angle here. We'll call this theta. Okay. Now if theta is measured in radians, what I've done, this angle has created an arc that is subtended. And this arc, the length of it would be very difficult to measure unless you're in radians. So I have some measure for my angle theta in radians, and the length of this arc will be exactly equal to theta. So this is the bonus to using radian measure. Now let's consider what will happen if we are on a unit circle. Now, how does the radian measures work? We know that a circumference of a circle is 2 pi times the radius. Now, if we're in a unit circle, remember the radius is equal to 1. That's why we have, this is the 0.10 and this is the 0.01. So the circumference would be 2 pi times the radius, which is 1, and the circumference would just be 2 pi. So that would be the distance around the circle. Now, if we're in radians, which we are, then that would mean this angle that completes one full rotation the angle that corresponds to that must also be 2 pi. Okay, a few other preliminaries that we can work with. If the distance all the way around then is 2 pi, we can think about this angle as 0 if you've gone nowhere, and then on one full rotation it's pi over 2. If you go halfway, you've gone the angle of pi, and if you go half of that, you're at pi over 2, and the one at the bottom is 3 pi over 2. These are for positively rotated angles. Okay, some other things that we need to know then. When we start talking about the quadrants, this is quadrant 1, it goes counterclockwise. This is quadrant 2, this is quadrant 3, and this is quadrant 4. Okay, so the angles that fall in quadrant 1, these angles, all of them theta, they have to be greater than 0 and less than pi over 2 if you want to be in quadrant 1. Okay, so let's begin the setup for the proof. We'll just look at the angles that are in quadrant 1. Okay. So if I just redraw the quarter circle, this is the 0.10, this is the 0.01. And I can put in any angle. Right? Let's call this theta. Okay. Now remember the length of this arc, because theta's in radians, will also be equal to theta. We will have cut this off. It will correspond to some point in the xy plane. And remember the x values correspond to the cosine of theta, while the y values correspond to the sine of theta. And you can see that if we were to drop an altitude here, we would form a right triangle, and the length of this side, being the y values, would be representative of the sine of theta. So in quadrant 1, what can we say? So in 1, we know that the angles must be greater than 0 and less than pi over 2. But here then we can start comparing the blue that I've just written here, this sine of theta, to this arc that is subtended. Okay, we can see then, I hope you can see, that 0 would be the lower bound for the sine of theta, and the sine of theta, the length in blue, will always be less than that arc that is subtended. Okay, so here we have set up our inequality that is true. 0 will be less than the sine of theta, which will be less than just theta. Okay. And this is what we'll use to prove the theorem, or to prove the limit using the squeeze theorem. So here we go. We're in the first quadrant, so we'll be looking at values of theta as they approach 0 from the right-hand side. Okay. So using the inequality, this inequality from here, what we can say then is that the limit as theta approaches 0 from the right of theta, that has to be less than, and the limit as theta approaches 0 from the right of the sine of theta. Now that's the one that's unknown to us, and we're looking for it, and that must be less than the limit as theta approaches 0 from the right of theta. And now we're just a few steps away. 0 is just a constant, so it will not change as theta is changing. So this limit here will not change. This limit is 0. That will be less than the limit as theta approaches 0 from the right of the sine of theta. And then again over here, as theta approaches 0, just by a direct substitution, this limit must also be 0. So now you can see that since 0 was less than the sine of theta, which is less than theta, this was an inequality that is always true. We can look at the values of the limit by the squeeze theorem, and this limit is squeezed in between 0 and 0. So therefore, by the squeeze theorem, the limit as theta approaches 0 from the right of the sine of theta must also be equal to 0. Okay, so this is our first result. Now we're looking for the full limit. We're trying to prove that the limit as theta approaches 0 excuse me, of the sine of theta is 0. So we have the limit from the right, now we need the limit from the left. So we are looking for the limit as theta approaches 0 from the left of the sine of theta, and we'll try and say something about that. Now, let's redraw the circle so we can think about what would be happening. If we want to approach 0 from the left, we need to be below that. And in this case, we'll be working with negatively rotated angles. So they will go the opposite direction. They will go clockwise. All right, and so now this would be the angle 0. This would be the angle negative pi over 2. Again, we can pick some angle that's negatively rotated. We will call this theta. It is measured in radians, so there will be the arc that is subtended that is exactly equal to it. And we could drop the altitude here and form the right triangle. And this side here would be equal to the sine theta. So in this case, when we're in quadrant 4, we could write the angles as that to be in quadrant 4, the lowest value would be negative pi over 2. That'll be less than any value theta in quadrant 4. And the highest value that it will take on is 0, because these are negatively rotated. But the same relationship between the sine of theta and theta will still be true. The sine of theta will be less in magnitude than the angle theta will be. Okay? But we're negatively rotated. So what does that mean? Theta will be more negative than the sine of theta, and those will still be negative because we're less than 0. Now, this is not the way I necessarily like to read these, because we have to keep in mind then that these are negative. So maybe it would be easier for us to think about it this way. 0 would be greater than the sine of theta, and the sine of theta will be greater because it's less negative than just theta. You can think about it either way that you like, but now we've set up, this is the inequality that we need to apply the squeeze theorem to, and we'll just take the limits now. So the limit as theta approaches 0 from the left of 0 must be greater than the limit as theta approaches 0 from the left of the sine of theta, and that has to be greater than the limit as theta approaches 0 from the left of theta. Okay, now let's do the direct substitution. Again, this is just the constant 0, so it doesn't depend on what theta is doing, and this limit is 0. That will be greater than the limit as theta approaches 0 from the left of the sine of theta. And here again, we can look, and the limit as theta approaches 0 from the left of theta is just 0. So again, by the squeeze theorem, the limit, as theta approaches 0 from the left of the sine of theta is equal to 0. And that's what we needed to show. Then, since the limits, the left and the right-hand limits agree, this means that the full limit does exist, and we can write the limit as theta approaches 0, the full limit of the sine of theta is equal to 0.